Okay, our next speaker is Noah Lebowitz-Lockard, who is speaking on factorizations into distinct parts. Please go ahead.
All right, so before I get into factorizations, hold on. There we go, okay. Before I get into factorizations, I'd just like to go over what a partition is. So I'm going to let P of n be the number of unordered partitions of n, and P sub d of n be the number of partitions of n into distinct parts. So a partition is just a way you can write n as a sum of positive integers. So for example, 4 has 5 partitions, 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 4 ones. So P of 4 is 5. But only 2 of these partitions consist of distinct parts, namely 4 and 3 plus 1. So P sub d of 4 is 2. One interesting fact about P sub d is that it's also equal to the number of partitions of n into odd parts. This is a nice proof either using the generating function, or there's a more complicated bijective proof that also works. And both of these functions actually do have nice generating functions. So in particular, here's the generating function of P of n. So this is the function P of 0 times q to the 0 plus P of 1 times q to the 1, all the way up to infinity. This first term counts the number of ones. So if we have 0 ones, we multiply by 1. If we have 1 1, we have q, 2 ones, q squared, again, all the way up to infinity. Then we do the same thing for the number of 2s, the number of 3s, number of 4s, and so on. Each of these terms is a geometric series, so we can write it more simply. And in particular, the partition function actually has this nice generating function that it's the product of 1 over 1 minus q to the m, where m ranges from 1 to infinity. The partitions into distinct parts have an even nicer generating function because we can truncate each of these terms. So first we decide if there are 0 or 1 copies of 1, 0 or 1 copies of 2, 0 or 1 copies of 3, and so on. So instead we get the product of 1 plus q to the m, where m ranges from 1 to infinity. And so these are very similar generating functions, which is what you would expect because they come from very similar functions, but they are ever so slightly different. And one of the first really big results on partitions was Hardy and Ramanujan's asymptotic formulas. So just using the generating functions, Hardy and Ramanujan found the asymptotic formulas for P of n and P sub d of n. And here they are. So P of n is asymptotic to 1 over 4n root 3 times e to the pi root 2n over 3. And P sub d of n is 1 over 4n to the 3/4 times the 4th root of 3 times e to the pi root n over 3. And so the main thing to notice is these different exponential terms, that this P of n has this extra root 2 in the exponent that P sub d of n does not have. So they're growing at e to a constant multiple of root n. And that's really the main, size of the asymptotic. And now we can generalize this to factorizations. So a factorization is just the multiplicative analog of a partition. So I'm going to let f of n be the number of unordered factorizations of n into parts greater than 1. And capital F of n is the number of such factorizations into distinct parts. We have to specify parts greater than 1 because otherwise we could just multiply by as many ones as we want. And so in that case, little f and big F would both be infinite, which would make them useless. So we have to specify greater than 1 in order to actually have useful functions that we can use. So as an example, here are the factorizations of 12. 12, 6 times 2, 4 times 3, and 3 times 2 times 2. Little f of 12 is 4. However, the factorization 3 times 2 times 2 has 2 copies of 2. So big F of 12 is 3. Again, I said unordered, so that's why I'm not also counting 2 times 6 or 3 times 4 or anything like that. And in 1924, McMahon observed that the Dirichlet series of little f into big F are actually very similar to the generating functions of partitions and partitions into distinct parts. So that's what you would maybe expect, because it is just a multiplicative version. And, I think of like a Dirichlet series as typically corresponding to multiplicative functions, whereas generating functions are more for functions defined additively. Here's the Dirichlet series of little f. So in particular, first we count the number of 2's. So if there are 0 2's, we just multiply by 1. If there's 1 2, we have this 1 over 2 to the s term. If there are 2 2's, we have 1 over 2 to the 2s, etc. Then we do the same thing for 1 over 3 to the s, or we do the same thing for 3. We have 1 over 3 to the s, 1 over 3 to the 2s, etc. And then we do that for every other number. Once again, these are geometric series, so we can simplify each of them. So we actually get this very nice product. We get the product as m ranges from 2 to infinity of 1 over 1 minus m to the negative s. And so if you recall from a few slides ago, the generating function of partitions was the product of 1 over 1 minus q to the m. So instead of q, we basically just have m down here. The Dirichlet series of big F is nicer than this because now we can only have at most one copy of 2, at most one copy of 3, at most one copy of 4, etc. So we get this nice product 1 plus m to the negative s as m goes from 2 to infinity. So these both have very nice Dirichlet series that are similar to the generating functions of partitions that we saw earlier. So using these Dirichlet series, Oppenheim found the sum and maximal order of little f of n. So in 1926, he showed that the maximal value of little f the maximal value of little f of n for all n less than or equal to x is x over L of x to the 2 plus little o of 1, where L of x is this complicated quantity e to the log x triple log x over double log x. And this L of x term will actually come up later in this talk. I don't know. So we will see it again. It does come up a lot with partition functions and factorization functions. In the very next year, he found a formula for the sum of little f of n for all n less than or equal to x. So we got this formula down here, 1 over 2 root pi x e to the 2 root log x over log x to the 3/4. And he got both of these just from the Dirichlet series that we saw in the previous slide. So it really is a powerful tool. And this was only slightly after Hardy and Ramanujan's asymptotic formulas for the partition function. Unfortunately, that first formula I just showed you actually has a mistake in it, and it wasn't found for 57 years. In 1983, Canfield, Erdős, and Pomerantz corrected Oppenheim's maximal order for little f of n. In particular, they showed that the exponent of L of x should be 1 instead of 2. So it's a fairly minor change. He did have the correct general shape of the formula, just that the exponent was off. So they also generalized this to big F of n as well, which hadn't previously been known. So the maximal orders of little f and big F of n for all n less than or equal to x are both x over L of x to the 1 plus little o of 1. And so it actually shows how close together these functions are, that they have basically the same maximal order. That the ratio between the maximal orders is still L of x to the little o of 1. So this is really useful if we want to bound little f of n in general, but what if we wanted to bound it for a specific value of n? And this problem had not actually been investigated until very recently. So just for some notation, I'm going to let n equal p sub 1 to the alpha 1 times p sub 2 to the alpha 2, all the way up to p sub r to the alpha r. And our goal is to bound f of n in terms of this vector I'm calling alpha, which is just alpha 1 through alpha r. So it shouldn't depend on any of these prime factors, just the exponents. Interestingly enough, though, for ordered factorizations, this problem has basically been solved already. This was actually in 2008. Delaglease, Hernane, and Nicholas found very precise bounds for the number of ordered factorizations of n entirely in terms of the exponent. So, as I said before, for unordered factorizations, this problem hadn't actually been investigated until very recently. So in 2017, Balasubramanian and Srivastava found the following formula. So let Z be the unique positive solution to this equation right here. Z is the product of 1 plus alpha I over Z as I ranges from 1 to R. So recall that these alpha I's were the exponents in the prime factorization. It's not immediately obvious that there's one positive solution to this, but what happens is Z is actually increasing. That's an increasing function, but this product on the right is decreasing. So initially, for very small values of Z, this product is much larger than Z, but eventually Z is increasing and the product is decreasing. So there is exactly one positive solution, and we call that Z. And then we're going to let N be the floor of Z. And so these two authors obtained this lower bound for little f of n. So it's this whole term over here times the product of 1 plus n over alpha I raised to the alpha I plus 3 halves as I ranges from 1 to R. So it's actually fairly close to just the original definition of Z, but with some of the terms, with this alpha I over Z just flipped upside down, and then this whole exponent here, and then these other terms on the left. So this is all well and good, but they never actually found upper bounds for little f or big F. So there really weren't any, upper bounds known except for that one we saw a few slides ago, which was n over L of n to the 1 plus little o of 1. So I've been investigating this problem recently. So in order to find the upper bounds, we use what's known as Rankin's trick. So how does Rankin's trick work? Well, Rankin's trick is a tool that lets us turn Dirichlet series into upper bounds. So let's say that H is a non-negative arithmetic function. For all n, we're going to have that H of n over n to the s is at most the Dirichlet series of H. And this looks very complicated, but the basic idea is that we're just taking one term from this sum. And because we know that all the other terms are non-negative, we know that the sum has to be an upper bound. So then we multiply both sides by n to the s, giving us H of n is less than or equal to n to the s times the Dirichlet series of H. And then we choose s to minimize this upper bound. So you have one variable that you can control in order to minimize the upper bound. And so this just turns into an optimization problem. But if the function is not as well understood as its Dirichlet series, you can use the Dirichlet series very effectively. And so this has been used for bounding all manner of functions over the past century or so since Rankin came up with this trick. Here's what this looks like for big F of n. So I'm mainly going to focus on big F of n, which corresponded to factorizations into distinct parts, just because the Dirichlet series is a little bit nicer. So applying Rankin's trick to big F of n gives us this formula, that it's at most n to the s times the product of 1 plus 1 over m to the s as m ranges from 2 to infinity. But here's where it gets interesting, because we can do better. We don't just have to stop here. Why do I say that? Because n has this very specific factorization, which means that every factor of n also has a specific factorization. In particular, it has to consist of the primes p1 through pr. It can't have any other prime factors. So I can write any factor of n in the form p sub 1 to the beta 1, p sub 2 to the beta 2, all the way up to p sub r to the beta r. And where beta is just some tuple of non-negative integers. We can also impose the additional condition that each of these beta i's is less than the corresponding alpha I, but this doesn't actually substantially improve the bound. And I'm going to let beta just be this vector beta 1 through beta r. So we can restrict our factors and get a superior upper bound, because now we're no longer taking this product over all possible values of m. We're only taking the product over all values of m that are with prime factors p1 through pr. So we restricted our product. So this Dirichlet series technically only applies to factorizations, or it only applies to numbers consisting of the prime factors p1 through pr, but that doesn't really matter for our specific value of n. But then we can, so here's what we have, but then we can do even better than that. Because there's actually something very strange about this upper bound. And no one had really considered what the implications were until recently. But the upper bound depends on P1 through PR. But big F of n doesn't depend on P1 through PR. It only depends on the exponents. So in theory, our upper bound shouldn't actually depend on the prime factors of n either. It should only depend on the exponents of the prime factors. So an upper bound of this form is still going to be suboptimal. And so here's the clever trick that's actually similar to something that Balasubramanian and Srivastava had done in their work, which is instead of using P1 through PR, I'm going to create a new set of variables called Q1 through QR. And we're going to replace each instance of pi to the s with q sub I. Then we're going to optimize those q sub i's. So I'm going to let q be the vector q1 through qr. And then we're going to, in a sense, factor n into these variables. So we actually get this much nicer generating function where this is taken over every possible R tuple. So this term right here, so we have f of n is less than or equal to q to the negative alpha times the product of 1 plus q to the beta, where beta ranges over all vectors of, over all R tuples of non-negative integers. So this q to the negative alpha really represents q1 to the negative alpha 1, q2 to the negative alpha 2, etc. And this q to the beta represents q1 to the beta 1, q2 to the beta 2, all the way up to qr to the beta r, etc. So we get this much nicer upper bound for f of n that I think just feels a lot cleaner, simply because we're combining all these terms. But this is also better because it no longer references specific primes anymore. It references these R variables, which we now get to optimize. So before we could only optimize one variable, and that was the variable S in our Dirichlet series. Now we can optimize R variables, which gives us a lot more control. So unfortunately, I found this upper bound very difficult to work with. And we can replace it with e to the q beta. So I'm just using the fact that for any given x, 1 plus x is less than or equal to e to the x. These values of q typically tend to be fairly small. So we're not actually losing a whole lot. And now we have this new expression for f of n. So big F of n is at most 1 over e times 1 over q1 to the alpha 1, q2 to the alpha 2, all the way up to qr to the alpha r, times e raised to this product right here, 1 over 1 minus qi, as I ranges from 1 to r. So that's corresponding to every possible R tuple that we had up here, and it works out to be a nice Dirichlet series, or works out to be a nice product of geometric series that we can then optimize. And now we can actually find the values of q. And amazingly, it actually comes back to z, which we saw earlier. So we saw that z was the unique positive solution to the equation z equals the product of 1 plus alpha I over z, as I ranges from 1 to r. And we get q sub I is alpha I over z plus alpha I. So we never should have been factoring into primes in the first place. In a sense, we should have been factoring into these q sub i's, which happen to have this nice formula. Then when we plug it back in, we obtain a new upper bound for big F of n. We get big F of n is at most e to the z minus 1 times the product of 1 plus z over alpha I to the alpha I as I ranges from 1 to r. And so this is actually very similar to the lower bound that we got for little f of n, which provides further evidence that these functions are typically very close together. I'd also like to point out that if z is smaller than some alpha I, this bound is accurate to within a factor of e to a constant multiple of log n over double log n. So previously, there wasn't an upper bound for big F of n that had this level of accuracy before. And it's actually fairly simple, or at least simpler than the lower bound for little f of n. After doing this, I also modified this technique to apply to little f of n, and we get a very similar bound. So now w is going to be the unique solution to this equation. It's the product of 1 plus alpha I over alpha 1 w. Here, I'm just assuming that alpha 1 is the largest alpha I for notational convenience. And then we get a very similar looking function for little f of n. So instead of z minus 1, we now have alpha 1 times w minus 1. And instead of z over alpha I, we now have alpha 1 over w over alpha I. So you get a very similar upper bound for little f of n. I then applied this to ordered factorizations of n into distinct parts. There weren't any good upper bounds for this either. So I obtained this formula down here, where v is the unique solution to 2 over 2 minus the product of 1 plus alpha I over v, that whole thing minus 1, and big G of n is at most this quantity. So for 3 separate related functions, we've obtained 3 very similar upper bounds. Each time it was 1 plus our desired variable over alpha I, and just the variable we're using each time has a slightly different definition based on the function. I don't have any sense of accuracy for big G or little f, but these are still new upper bounds for these functions. For the last part of the talk, I'd just like to shift gears a little bit and talk about some related research that I've also done with these functions. So I said that one would expect that little f of n and big F of n would be pretty close together. One reason for this is that typically a number doesn't have too many repeated prime factors. So I recently found this formula that little f of n over big F of n is at most 2 to the capital omega of n over 2, where capital omega of n is the number of not necessarily distinct prime factors of n. As an added bonus, we also get that 2 to the capital omega of n over 2 is at most root n. And so this is a nice upper bound for little f of n over big F of n. One interesting case is that if n is a power of 2, we can actually just calculate what these numbers are exactly, because if n equals 2 to the k, little f of n is the number of partitions of k, big F of n is the number of partitions of k into distinct parts. So just plugging in the partition formulas that we saw at the beginning of this talk, we get this whole formula. Why do I bring this up? Because I have also conjectured that this is the maximal order of little f over big F in the long run. So the heuristic argument for this is that this is when n has as many repeated prime factors as possible. So you would expect the ratio to be especially large in this case. I've actually checked this up to n equals 1 billion, and the largest values of little f over big F always occurred when n was a power of 2. So there is some computational evidence for this. That's when it is larger than all previous values of this ratio. And I'd like to close with one really interesting implication of this theorem. So earlier in the talk, I stated that Canfield, Erdős, and Pomerantz proved that the maximal orders of little f and big F are both x over L of x to the 1 plus little o of 1. However, only their lower bound for little f of n was constructed. The lower bound for big F of n was not. They never actually construct a value of n for which capital F of n is x over L of x to the 1 plus the low of 1. They only have an existential proof. But using the previous theorem, we can fix this discrepancy, because for the value of n they chose, capital omega of n doesn't have too many distinct prime factors, or it doesn't have too many prime factors, period. It has about log of x, triple log x over double log x squared. So by the previous theorem, the ratio between little f and big F is still L of x to the little o of 1. So their construction for little f also works for big F. So we now have a constructive proof. And so we've actually solved a nearly 40-year-old, a problem that was stated nearly 40 years ago with this theorem. And I would like to point out that if we assume the conjecture on the previous slide, we don't even need to do that whole argument with big omega, because then the ratio would just be e to a constant multiple of root log n anyway, just in general. Thank you.
Oh, thank you very much. Do we have any questions for our speaker? If not, thank you again.